Everyone and welcome back to SK1. In this video on analytical mechanics, we actually start integrating the equations of motion for any given mechanical system. We consider in the video a general case, and we'll also consider perhaps some special case like the harmonic oscillator, the simple harmonic oscillator. Now, the whole theory of small oscillations will quite obviously not be considered in the video, not for now, and we are not considering in a series of videos from now. After we are done learning the methods of integration of the equations of motion in Lagrangian mechanics, that is, we'll perhaps devote ourselves to the study of collisions of particles, the scattering of particles, and quite obviously before that, in the next few videos, we are also going to discuss about Kepler's problems and the two-body motion, the two-body problem, and only after all this will we, I suppose, take up the theory of small oscillations. So from now on, we start learning actually how do we integrate the equations of motion, and in the follow-up videos, the problems will be more related with the two-body problem, the Kepler's problem, is the motion in a central field and such, and then we take on the study of the scattering of particles. Now here we start with, well, first of all, Lagrange equations. For, let's say, n generalized coordinates. The thing is that when you consider the motion of a single particle in a conservative system, Lagrange equations simply reduce down to Newton's equations. So you have a single particle which is being acted on by some potential energy function. So it shares some potential energy function with some external field, and here the field is external. That's what we are talking about. So this is the form of the Lagrangian. You have a single particle, and how about we talk about the motion in one dimension only? We'll have to make it quite clear what exactly do we mean by motion in one dimension. Does it mean that we have to specify only one Cartesian coordinate? Well, not necessarily. That's how one would typically define it, and it's a fair definition for that matter. Landau defines it in a different way, and Landau says that if you have a single particle, so what motion in one dimension would actually refer to is that there are changes in only one generalized coordinate of that particle. So you have to count the degrees of freedom of a single particle, and the number of degrees of freedom of a single particle will correspond to how many dimensions the particle is moving in. So you need to choose a proper frame of reference, a proper coordinate system. That's the thing here. Let me consider the example of a particle moving on a circle, and here we have a particle . So to study the overall motion, the general motion of this particle, no constraints, let's say no external forces involved, there could actually be two generalized coordinates for this system. If you don't constrain it, that is, two generalized coordinates for this system. And you could either specify the x's and y's, or you could specify the r's and phi's. And either of them tell you where the particle is, and now we constrain it. Perhaps not constrain it, perhaps put it in an external potential energy function, in an external field, that is in some sort of external force field, such that it makes this particle revolve around the center in a circle with the same radius, with the given radius r. In that case, we know for certain that r doesn't change, that r remains a constant, or the time derivative of r is 0, and it is only phi that varies. So in this case, for one thing, the motion in x and the motion along y are not independent. They are well dependent on each other, because the motion happens to be such that x squared plus y squared is always a constant. So this equals r squared, and it's always a constant. So the motion along y depends on the motion along x and vice versa. So there's only one generalized coordinate here, and that generalized coordinate is phi. And how many degrees of freedom there are? Well, there is exactly 1 degree of freedom, because there is one generalized coordinate, or you could say it the other way around, that the number of generalized coordinates equal the number of degrees of freedom, or equal the degrees of freedom, because the degrees of freedom is itself a number. So you say that in this case, is the motion really one-dimensional or two-dimensional? If you consider a Cartesian coordinate system and watching this entire thing play off in a Cartesian coordinate system, you would really tempted to say that the motion exists, that the motion occurs in 2 dimensions, because the x's of the particle changes and the y coordinates of the particle change. But that is that you are really considering the Cartesian coordinate system to be a rather special, a unique coordinate system, which should not be the case. The laws of mechanics should very well be valid for all coordinate systems that you choose, and we often use the laws of mechanics in non-Cartesian coordinate systems. We will a lot of times use polar coordinates, as has been used here, or for the case of 3 dimensions, spherical polar coordinates or cylindrical polar coordinates, we might end up using sometime elliptical coordinates or hyperbolic coordinates. So when we say that the motion really happens in 2 dimensions here, because we are really choosing a Cartesian coordinate system to whip the entire thing play off, what we are really doing is we suggest that the Cartesian coordinate is more special than the other coordinates. So how about to state whether the motion happens in 1 dimensions or 2 dimensions, we chose that coordinate system in which consists of the generalized coordinates which describes the given particle, and that is, well, the polar coordinate system here that contains the generalized coordinates which are r and phi. So there is in total really 1 generalized coordinate, because you say that, well, r is really a constant here, and that, let's say, is a matter of constraint. So if you put on a constraint that r dot equals 0, so there's only 1 generalized coordinate phi, and this will choose this coordinate system to represent how many dimensions the motion occurs to, and 1 generalized coordinate, 1 coordinate that will varies. So we say that the motion really occurs along 1 dimension for that matter. Well, this is at least Landau's definition. So although the motion occurs in a plane and the x's and y's vary, there is 1 generalized coordinate. So I suppose it's a good definition to say that the motion actually occurs in 1 dimension only, and that is phi. Now you have a single particle, and the Lagrangian as well as kinetic energy minus the potential energy of its interaction with the external field, and then you put this in the Lagrange equations, and depending on the type of potential energy you obtain the corresponding equations of motion. Single particle, so its kinetic energy is really half times its mass times its speed squared. Now in an arbitrary coordinate system, this looks something like half a function of its generalized coordinate and the generalized velocity squared. In an arbitrary coordinate system, in a generalized, that is, now when I say arbitrary, you just cannot pick any coordinate system. Even though you could write the kinetic energy in those, when we are supposed to use Lagrange equations, we have to choose a generalized system. So minus potential energy of interaction with its generalized coordinate, which could quite possibly will depend on time, but we do not consider that case for once. I will later elaborate on that particular point. If let's say that the generalized coordinate is a Cartesian coordinate, and that is x, so we are talking about the motion along x-axis, well, in that case you find that the Lagrangian is simply half the mass. When the Cartesian coordinates are x, this function is but simply a constant, a property of the material itself, a property of the object itself, and that is the mass of the particle. We have x dot squared minus the potential energy of interaction along x. Now here I supposed that given that there is only 1 generalized coordinate in the system, 1 degree of freedom, the potential energy of interaction corresponds to the interaction of the particle with the external field along this dimension, along this coordinate axis, and in this case it's x, so it's really the potential energy as a function of x. And you actually need to, well, again, remember exactly how we got this form of the Lagrangian for a mechanical system that is open, that interacts with its environment. Because the first Lagrangian form that we wrote was, well, again T minus U, but here U was the potential energy of interaction within the system. So that was the Lagrangian of a whole closed mechanical system. But when you place a mechanical system in an open field, in an external field, then we figured that since the motion of the environment is, well, given to be definite, we know how it affects the motion of our particles, is given to be definite, we can, well, simply take away the terms that correspond to the motion of the environment from the Lagrangian of the whole system, and that will simply give us the Lagrangian of this particular system that we are dealing with, which is, well, which happens to be open because it's interacting with the environment. But then you must remember that this could as well depend explicitly on time for that matter, and this really happens to be the potential energy of interaction of how the motion of the environment, well, affects the motion of this system here. And it can only, well, at least in classical mechanics, be a function of these coordinates, so that has to be kept in mind. And this is why it's a function of the coordinate of the particle, generalized coordinate, that is because we considered back then everything in generalized coordinate, which in this case is the Cartesian coordinate x, so it is u of x over here. Now since this is a Lagrangian, if you substitute it into the Lagrange equations, well, what do you get? For starters, the time derivative of the generalized momentum is now simply the time derivative of what? It's the time derivative of linear momentum. Don't believe me? Well, let's try it. Partial dl over this is now dx dot. So it's now mx dot. You take the time derivative, constant mass, so it's mx double dot equals partial dl over dxj dqj, and which in this case is again x. So that becomes, this is explicitly independent of x. So it's only this term over here minus partial du over dx. And we are restricting ourselves to a single dimension. We don't even speak of any other dimension in this particular case. So you might as well regard this as a total x derivative. And that is the force acting on the particle along the x-axis, and so the force equals mass times its x-acceleration. Those are Newton's equations. So given that in this particular case of a single particle that moves in an external field corresponding to this potential energy of interaction between the particle and the field, Lagrange's equations simply reduce down to Newton's equations. Well, what is, for starters, the point of having Lagrange's equations in the first place if we are going to anyway solve the Newton's equations? Except that the Lagrange's equations directly derive from the stationary action principle, which gives us deeper insights to how classical mechanics really works. So the point of that really is that this is a very special case that we considered. For once, it's a single particle. Secondly, it's a single particle interacting with an external field, but the motion is along one direction, only one dimension. And thirdly, the motion is along one dimension, which happens to be a Cartesian coordinate. If you use non-Cartesian coordinates, these equations simply don't reduce down to the same form as Newton's equations. And on top of that, if you use a coordinate system which is in a non-inertial frame, then it quite obviously does not reduce down to Newton's equations, because Newton's equations do not work in non-inertial frames. You have to resort to pseudo forces to make them work, and this is something that troubled Newton. He wanted to figure out what frames do his laws actually work in, and so Newton wrote down his second law of motion first. And when he wrote down his second law of motion, he knew it for a fact that the second law of motion is not universally valid, because there are things that there are motions and there are accelerations he cannot explain, because they do not correspond to any interactions. They are not an effect of any interactions. If you yourself, if the frame of reference itself accelerates, then you know for the matter of fact, as a matter of fact, the object that it watches, the object that it observes, that object will quite obviously accelerate in the opposite direction. That is without the means of an external interaction, without the means of a force. So the second law of motion does not remain valid in a non-inertial frame. in an accelerating frame. But how do you make that distinction if all motion is supposed to be relative? So Newton pondered over it, and as I recall having read, it was some 17 or 19 years later that he came with the first law, and he says, well, here's the first law, and this is the definition of the kind of frames that the second law is valid in, and that is inertial frames. Lagrange's equations hold irrespective of what kind of frame you are using. So for this particle, when we talk about this particle moving in an external field, the Lagrange's equations, that is a Cartesian coordinate, Lagrange's equations will simply reduce down to Newton's equations. In a lot of cases, in fact in most actual cases, for solving most non-trivial problems, you will find that Lagrange's equations are far more helpful and they give you far deeper insights than Newton's equations. And the next thing, that how about we consider closed mechanical system? So the form of the Lagrangian looks quite the same, except this is the potential energy of interaction of both parts of the system. Let's say you have two interacting particles. Now what? Well, if you have two interacting particles, then there are total 6 degrees of freedom considering 3 dimensions of space. Let's say that there aren't really 3 dimensions of space, there's really 1 dimension of space. So you still have 2 degrees of freedom, but I don't think it's fair to say that, because you have 2 particles and they could rotate around each other, they could orbit each other, so it's not really fair to reduce it down to, well, 1 dimension only. So we have 2 dimensions of space, and for that matter, this is the potential energy of interaction between them. For there are total 4 degrees of freedom here, and thus the Lagrangian is, for starters, half mass of first particle times the radius vector of first particle squared dot squared plus this thing minus a function of these two. And now here we are really considering a closed system and the interactions are completely external, and we want to figure out what these as a function of time are. So in this case, do Lagrange's equations reduce down to Newton's equations purely? Well, since we are going to be solving for each of these are really contain 2 components, and this is 1 x component and this is 1 x component, and here's 1 y component, there will be total of 4 Lagrange equations in this particular case. Now Newton's equations are themselves vector equations. So how about this? I want to write what Newton's equations would look like for this particular system, and I say that this is the kind of interaction, and this is with respect to what interactions. I think I need to be quite clear on this. Let's try to write it such: force acting on the first particle is equal to mass times second time derivative of the position vector of the first particle. And what is the force acting on the first particle? Force acting on the first particle should look something like this. And this term really corresponds to both the particles at once. So minus partial du over dy. So I can write this thing as a gradient in the first particle's well motion coordinates the potential energy of interaction between them. And similarly, you have for the second particle, this should be the kind of equation that we see. Correct? Yes, that seems to be about right. Now this itself is really 2 equations because there are 2 dimensions. So these are in x's and y's and these are in x's and y's. But the equations, I think, do look coupled, and the equations really are coupled. So for that matter, these things for general potential energies could get quite complicated, and then you find immediately that Lagrange's equations, since they really resort down to, well, the kind of generalized coordinate and generalized velocity that you're using, and those are the kind of things that we use, look far more beneficial in such cases. So that's the kind of thing that we have to keep in mind, and we'll actually solve such kind of problem in the next video, the 2-body problem, and we'll see how beneficial they really are. We can put these to a test. Now the next thing that we do is, do we exactly have to integrate the equations of motion in all such cases? You don't exactly have to write the Lagrange equations and integrate the Lagrange equations in all such cases, because we already have the first integration of the Lagrange equations, and we have gotten 3 conservation laws, and those are the conservation of energy and the conservation of linear momentum and the conservation of angular momentum. So a lot of times we can derive a lot of useful results from these principles only, and let's actually try it. So the previous case that we took, a particle that is moving in an external field, and this is the Lagrangian that the particle has, and the kinetic energy is simply half mx dot squared, and this is a function of x only. So the total energy of the particle in this case is, I shouldn't just say particle, the whole particle and the external field combined, T plus U, and we know that this thing really remains a constant. So half mx dot square plus u of x is equal to E, which is a constant, and that is determined by the initial conditions of motion. So if it is determined by the initial conditions of motion, a lot of times we actually have the knowledge of what initial conditions are if we are going to solve the problem, and if we know what the initial conditions are, we as well know what the initial energy of the system is. And given that the system is symmetric in time, so I shouldn't say symmetric, that the system, if you look at how the system varies in time, the Lagrangian of the system does not explicitly depend on time. So the equations that go on the system are invariant under any time translation, and that tells you that energy should be conserved as per Noether's theorem. And so if energy is conserved, this is what energy the system began with. There should be the energy at all external times. So this really is a constant, and it is a constant corresponding to initial conditions. So we should treat it as a constant, and then we can derive a lot of useful results, such as, first of all, what's x dot square as per this equation? E minus u twice of this over m twice of E minus u of x over m, and then we have the square root of this thing that gives us x dot. So dx over dt equals this, we have dx on the other side, then dx over dt equals this thing. So dt over dx equals the inverse of this thing, and that goes something like a square root of half m, and the square root of, here we have dx over the square root of E minus u of x. So all the x's on one side, the t on the other side, and then we actually go ahead and integrate this thing. Now quite obviously, without knowing what u of x exactly is, we cannot integrate this thing. So we find that integral of dt, and it's an indefinite integral, I don't set any limits. So this is an indefinite integral plus an arbitrary constant. I shift it to the other side for reasons you shall know. I could as well have kept it on this side. And this is what we obtain by simply using energy conservation, given the fact that we knew that energy conservation is valid for this mechanical system. And energy conservation is a rather universal system. So in all of the classical mechanics we'll study, fundamentally speaking, energy remains conserved. It's just that a lot of times we'll encounter such parts of the system that we have to study that energy will not be conserved individually for that. Now here, there's a constant. The significance of this constant is that, well, it does not really matter that when you, what is the initial instant when the motion starts. That's the significance of this constant. I think I've explained this before, that you can start your clock now, you can start your clock some 10 seconds later. So it does not really matter. The equations of motion do not contain time explicitly. And that is if it was something like 5 seconds on the clock when the system began moving, or it was something like 10 seconds or 15 seconds, or the clock read t equals 0 when the system began moving, it does not really matter. All that matters is the time difference that elapses between two time instances. All that matters is the time interval, not exactly the time instant. Thus, there is an arbitrary constant here which keeps things unaffected. You can as well set that thing to 0, does not matter. But I think it is advisable to keep it here. So if you're considering actually the limits of integration in a given system, then you can determine what that constant should be accordingly for matters of convenience. So what does this equation exactly tell us? Well, as I mentioned, that energy conservation is itself a first integral of motion. And well, so is linear momentum. So are linear momentum and angular momentum conservation. This does tell us the same things that solving Lagrange equations would do, except that not at all times in the same convenient way. If you want to figure out, let's say, what the time period of oscillation of some mechanical system is, so this equation can very well tell you that straight up, and you don't have to solve Lagrange equations in those ways. And how do you do that? Well, first of all, when is the motion of a system oscillatory? And that is, it goes back and forth between 2 points. And we can actually figure that out for a lot of cases, and I'll talk about it shortly. But for now, let's just look at it and see that what's the difference. This will give you t as a function of x, and what difference does it make as having x as a function of t? So if we have x as a function of t, you could have, well, 2 points in time where you have the same values of x. So 2 points in time give you the same values in x. And if you consider that, and that is quite common case, I mean, you have the simple harmonic oscillator, let's consider spring, or on a block, or you have the simple pendulum. So there are 2 points in time, there are infinitely many points in time where the pendulum bob passes through the same points. But if you inverse this function, so you get t of x, and this looks a little troublesome because for one value of x there correspond 2 or more, in fact perhaps infinitely many instances. So that is not really a function, is it? It's not a function technically. A function is defined to be such a mapping such that for a given value of its input, it will give exactly one in output, not more than that. So that is a little troublesome. So you have to consider this thing does not really give you a function of x. I should mention that, even though it does look like. You have to keep a notice of this. We have carried out the integration in x already. We have carried out the integration in x. This gives you more like a function of energy. But then you say that energy is a constant. Well, energy is a constant given the external conditions of motion. For all mathematical purposes, it's still a variable because you could have started it with this value of energy and that value of energy. So this really doesn't give you a function of x, it does give you a function of energy. That the various time instance, and I said that this equation will tell you a given time interval between 2 points, that the system passes from this point to this point. What is the time interval needed for that? That's what this equation tells you, to pass from one point to another, or vice versa, back and forth, I mean. So it will tell, this equation will tell you that given this value of energy, it could have taken this much time. If given this value of energy, the system takes this much time, and given this value of energy, the system takes this much time to pass through these 2 points. And that is quite obviously given this condition, that this is how the particle interacts with the given external field. So the time interval really is a function of energy that has to be kept in mind. Next, we actually go ahead and discuss about, and we'll put some use to this particular thing, and we'll perhaps consider simple actual integration of the equations of motion of, let's say, the harmonic oscillator. That will be at the end of the video. Let's consider these cases. How you can simply look at a potential energy curve and determine the possible motions of the system. I'll consider a potential energy curve. This is u of x, this is x, and we consider the same system, a single particle moving in the influence of this potential energy. And let's say that this is a potential energy curve. Well, potential energy has the same dimensions as total energy, you know that for a fact. In fact, you can map the total energy on the same thing, and we say that the total energy is really a constant. So how about this? That this tells me what the total energy is. This line tells me what the total energy is. Why is it such? Well, we have a potential energy curve, and for for all values of time, we know that the energy remains the same, so it really is a constant. So I say that, well, how about I draw a line on this curve that tells me what the total energy of the system is. And the next thing that we do is that since the total energy is a function of kinetic energy and potential energy, and this goes something like the sum of over all particles half times mass times its x speed squared, and this is the square of a real quantity, thus it is always positive. The mass is always positive for a particle as per the stationary action principle. I have explained it. Masses cannot be negative as per stationary action, and thus the kinetic energy is always positive. The fact that the kinetic energy is always positive means that whatever the potential energy be at a given point, in space or time, the total energy has to always be greater than the potential energy. That's what this tells us. Or in the extreme case, when the kinetic energy happens to be 0, the total energy equals the potential energy. Now the thing is, it does not necessarily mean that the total energy has to be always positive. Let's say that the potential energy is very much negative, so it has a large value with a negative sign, so that could make the total energy still negative, but it will always be greater than the potential energy. In the extreme case, I wouldn't call it a trivial case, which is why I'm calling it extreme. Since you're essentially adding a positive quantity to it always, it is always greater than or equal to the potential energy. When it equals the potential energy, then the kinetic energy is 0. So if you look at this graph, and I say that this is the kind of graph we have of potential energy of a given, that of the potential energy of interaction of a particle, the particle that we have been considering up until now, of its interaction with the external field, this is how it goes at various points in space. And then you say, well, this is the energy that the particle started with. It could have started with some different energy. Since the total energy is really an integral of motion, and thus a conserved quantity, an integral of motion, and all these integrals of motion will depend on the initial conditions of motion. So even though it can be written as the kinetic energy plus the potential energy of particle, it really is a property of how the motion began. That is what the energy has to do with. And afterwards you come up with it, it can be written as the kinetic energy plus potential energy. And given that we know how the system began, we can map this total energy onto this diagram, and we can well figure out what the possible motions of the system. We know that the system cannot move between these 2 points. Why can it not move in this region? Because this vertical thing is really a potential energy graph. Horizontal can tell you, horizontal line is where the particle is, where it moves, because that's the x-axis along which the particle moves. The particle cannot move in this region. And why not? Because this is the line of the total energy, and the potential energy in this region exceeds the total energy at all points. And we know for any real motion this cannot be possible. The total energy has to be greater or equal to the potential energy. So the system cannot move between these 2 points. This is a forbidden region. How about these 2 points? Let's first of all eliminate all possible points where the motion cannot occur. Let's see, the system cannot move between these 2 points either, because again, for the very same reason, if we talk about motion between these 2 points, it is quite possible. It could quite possibly happen, and the reason is because at all points here, the potential energy is always less than the total energy. But there's more to it. At these 2 points exactly, the curve and this energy line intersect. And you know that when the energy is equal to the potential energy, the kinetic energy is 0. So if you have a system that starts as motion with this value of energy, and that starts as motion in anywhere this region, at any point in this region, you know that what will happen is that the system necessarily comes at rest at this point. It is a necessary case. And the system will also come at rest at this point. So these are where the speed of the system, these 2 points are where the speed of the system speeds are 0, and they are called turning points. These are the turning points, because this is really where the system takes turns. Now why must it take turn? Because if you look at this point, then the potential energy falls towards the x direction, and given the system is at rest at this point and the potential energy falls, it tells you that a drop of the potential energy exerts force on it towards the right, and so the system will be exerted on by a force at this point, and then thus it starts moving here. And as it starts moving here, it loses its potential energy and gains additional kinetic energy till it hits the lowest point of potential energy, and it is at this point the system will have maximum kinetic energy. And what will, because the potential energy here is really 0, so it will have its maximum kinetic energy at this point. And what is the kinetic energy really? It's the total energy minus the potential energy. So how much kinetic energy does it have? Well, this is the total energy, this is the potential energy at this point. So this difference in values is how much kinetic energy it possesses. Next we go here, and as it goes here, since it has a kinetic energy and it's moving in this direction, but the potential energy drops in this direction, so it's moving towards ascending potential energy, but it drops backwards, so there's a backwards force on it, and it moves until the potential energy and kinetic energy and total energy are again equal. It has 0 kinetic energy now, and it comes to rest. Potential energy drops in this direction, so it moves again, and it keeps moving. And this is an oscillatory motion. And oscillatory motion is whenever a system goes back and forth between 2 points, between 2 configurations. So this is an oscillatory motion. And you can tell that whenever there's a system that moves between 2 turning points, and that is between 2 points where the potential energy and total energy are equal, the motion is essentially oscillatory. And an oscillatory motion is a bound motion, it's a bounded motion, because then the system cannot move off to infinity. These are 2 actual turning points, and it will always be moving off only in this region. Thus an oscillatory motion is always a bound motion. It cannot move here. How about the system started to begin with at this point? And if it starts at this point, let me make this thing such. Alright, clearer that the potential energy keeps falling. If the system starts to begin with from this point, it has to have 0 kinetic energy. So it starts with 0 kinetic energy because the potential energy and the total energy equals 0. And if it starts from this point, this is where the potential energy drops. This is where the system will accelerate. So it gains energy in this direction, and it gains energy, and it gains energy. And you can see that even though the rate at which it gains energy might diminish, I wouldn't exactly say diminish, the rate might slow down, but it keeps doing that forever, and that is, it keeps gaining kinetic energy because the potential energy keeps falling, and it keeps falling towards negative values. It keeps moving forward. So if the system is not between 2 turning points, this is quite possibly a turning point. This is one turning point, really, because the 2 energies, potential and total, are equal at this point. So if the system were to say start from here, and the only way that the system would start from here and actually reach this point is that you have imparted enough kinetic energy in it already, and that is, its motion is in this direction, that it will actually reach till this point. So if the system starts from here, let's say, and it goes over here and it goes over here. So, and this is the total energy that the system initially has. And that would really mean that you have to set the kinetic energy to a certain value at this point, so that this is still the total kinetic energy. This will be the turning point of the system. It again goes to rest at this, and then it will come back in the same direction, but it won't stop here. It will keep falling and it continues to move to the right. So even if you let it move in the opposite direction towards this point, with this given value of total energy, the motion is unbounded, because it will eventually turn around again, and there is no turning point in that direction. It is an unbounded motion. These are also called infinite motion. Similarly, if this case the potential energy keeps dropping, it does not, there's no other turning point, well, at least from what curve we see, and the system will keep falling in this direction. So even if it starts from here and it moves over here, it will eventually, with this value of energy, come to a turning point, turn around, and it keeps falling backward. So this way you can tell if a motion is oscillatory or not. If there are two turning points for the system, the motion is necessarily oscillatory. You can tell what the forbidden regions are. The system cannot move in this region, because to move in this region it had to have a higher level of energy, which it does not possess. This is the value of energy it started with. So keep in mind, the energy, the total energy, is the property of the initial conditions of motion. As the energy started with, it does not have that energy, well, it cannot go to that region. Thus that is a forbidden region of motion. Next, let's talk specifically about oscillatory motion, and let's see, we can find what is the time period of a given oscillation or oscillatory motion. And what that basically means is that if the system, let's say, starts from one point, and not necessarily the initial point, you consider any arbitrary point, let's say x0, and so what is the total time needed for the system to return back to S0? Since the motion is oscillatory, it will pass through all these points indefinitely, infinitely, through the same given points in this particular case. So what is the time needed for it to come back to x0? That is the case we imagine. So how about, instead of x0, we actually simplify this and we talk about the boundary points only, the turning points. And let's say that the turning points are x1 and x2. So I imagine the same graph again, u of x, x here. This is the given value of energy the system started with, and the curve of the potential energy is this. So in this case, maybe there are other possible motions over in this direction. We concern ourselves whether the system started between these 2 points. So this is one of the possible regions of motion. This is a forbidden region. This is all a forbidden region. This is perhaps a given motion that is possible, but from the looks of it, it looks an infinite motion. This is an oscillatory motion. Consider this to be the point x1. Consider this to be the point x2. The system starts, let's say, from point x1. It could have started in anywhere between these 2 points. Let's say it starts from x1. So what time does it take to return back to x1? So it first goes here, stops at x2, and then comes back at x1. Now here the motion is quite symmetrical between these 2 points, quite symmetrical about the point between x1 and x2, but that necessarily does not need to be the case. So we consider a very general example of such a kind of oscillatory motion. So how about trying to figure this out? Well, we know that the previous formula, that the time interval could be given, and that is from energy conservation law only, from such a kind of formula plus an arbitrary constant, and that could give you any time instant given this arbitrary constant that is set by the initial limits of condition of the motion, at what, well, the system starting with this particular value of energy could have traveled between 2 points. And so for that matter, I think it is quite better to write this as this kind of integral. We want to figure what the total time to go from this point and back is. Now remember that the kind of frames that we have been considering, well, time is an isotropic frame. I don't think you would call it a frame, let's call it a dimension. Time also has this isotropy property that if a given motion is possible, its reverse motion is also possible, and it will turn out to be exactly the same. So if you have a system and that goes through some specific sets of processes and you reverse all the velocities and the system is not complicated enough, or the thermodynamics enters equations and messes all this reversibility. So if you have a given system, since we are considering fundamental physics, and so you have a given system that is simple enough that thermodynamics does not need to well be considered, then a given motion is possible. You reverse all the velocities, so the reverse motion is also possible. So the system really is reversible in time. And that tells you that if the system started from x1 to x2, I could actually divide this motion from x1 to x2 to x1 back into in two parts. First, that it goes from x1 to x2, and second, it goes from x2 to back to x1. And I want to figure out what this total time from x1 to x2 to back to x1 is. So we say that is started with from x1 and goes to x2. How about we reverse all this direction of time and all the velocities and everything, and the system started from x2 and it goes to x1. The system has reversible dynamics, and so the time that is needed to go from x1 to x2 should be the same as the time that is needed to go from x2 to x1. And this has to do with that the equations, the Lagrange equations or the fundamentals equations of mechanics are time reversible. So the time that is needed to go in this, let's call it capital T naught, the same as the time needed to execute this motion, capital T naught. So the next thing that we have to do is simply calculate the time that is needed to go from this point to this point and double it, and that is the time needed to go from here to here back here. Alright, and the reason we do have to consider is because if we want to consider, well, what is the time in interval needed for the system to go from x1 back to x1, and you place these limits here, this tells you the low and upper limits are same, so the integral will give us 0, and we do not need that. We need them to be different limits. And this is why we broke down the system in two parts, and this is a nice breakdown between the turning points only, that we can exploit this symmetry, time symmetry of the equations of motion. So the total time period, let's say that the system is at time t is equal to 0 when it is at x1, and it is at some capital T naught when it goes to x2. So this is the time needed to go from x1 to x2. So T naught comes out to be square root of, well, half m, the integral to go from x1 to x2, and dx over square root of e minus u of x, given this particular value of energy. So we are really calculating it as a function of energy, as a function of what the initial conditions of motion are. And so the total time to go from x1 to x2 and back to x1, let's call it capital T, as a function of this given value of energy is twice of this. So here we have a square root of half, you double it, so you have the root 2 in the numerator, integral x1 to x2 dx over square root of e minus u of x, and this will tell you for any given value of potential energy what the time period of oscillatory motion is, provided that the motion is oscillatory, which we know here for a fact, and that is by looking at what the potential energy graph looks like. So it's important that the motion be oscillatory for the formula to work at all. So that's what we find here. Now, and that tells you that this formula is actually useful, and where it's most useful is really where the motion is oscillatory, because it tells you this. As a whole, is how valid is this formula really? Well, it can really tell you time intervals only. It tells you the time intervals that is needed to go from one point to another. Even if the motion is not oscillatory, you can still consider 2 points, and this formula will tell you what time interval is needed to go between these 2 points. and that is a really useful quantity for that matter. It is a very useful result, and we have gotten this from the fact that energy conservation is itself the first integration of motion, and then we carry out a second integration. Well, quite generally we write the second integration of Lagrange equations, and this tells you. However, if you want to figure out what exactly is the motion of the system, that is what is the generalized coordinate as a function of time, what are the generalized coordinates as functions of time, so you'll have to explicitly solve the Lagrange equations. That is, let's consider simple cases and make the distinction. It is also important that even if this formula were to tell you what t of x is, it is oftentimes very difficult to inverse the function to tell you what x of t is, or t of q and q of t. Consider the harmonic oscillator, half m x dot squared in one dimension. Harmonic oscillator in one dimension, it is the Cartesian coordinate only. Well, I told you for such really simple cases, and keep in mind that this is the kind of thing you are seeing where momentum conservation will not look to be valid. And why is that the case? Well, that is really the case. It's not x dot squared, it's x squared, because you have put the system in an external field, because the field is external, keep in mind. How about the block on the spring case? Well, the field is itself is external for all mathematical and physical purposes. And how about this, that we write the Lagrangian of the whole block and the spring alike? Well, the spring isn't exactly massless for physics, is it? It still has some mass, and if you have to account the momentum of the spring because it moves and it has masses, you would find that in this particular case momentum conservation is quite clearly valid. It's just that you're making this assumption that the spring is massless, and from that assumption it stems that, well, even though all the dynamics are internal for the system, still momentum conservation seems to be violated. No, you're ignoring the momentum of the string. That's why it looks like. And so if you actually want to talk about what kind of system a spring on a block is that is executing harmonic oscillation, so what it really is that a single block, and that is the only system, and its interactions with the spring are external interactions, and so you must treat it as external interactions for the physics to make sense while assuming that the spring is massless. You must assume it to be external interactions. That is what we do here, but we do not restrict ourselves to the spring system. So this is the Lagrangian, and as I told you, for all such cases, for these kind of cases, external interactions, one dimension, Cartesian coordinate is the generalized coordinate, single particle. So for these interactions, the Lagrange equations simply, for these mechanical systems, simply break down to Newton's equations, and it will simply give you this thing only. What is now minus partial du over dx, and this is basically mx. What is it? Alright, do I actually have to integrate this? It gives you something like, it isn't m, my bad. We use a spring constant k, and it gives you something like kx, right? Minus, with a minus to it. And so here, these are the equations of motion. The Lagrange equations give you the equations of motion, which in this particular case just happen to be Newton's equations. So the integration of Lagrange equations here is really an integration of Newton's equations. And how do you do that? Well, now we have done all that we had to do, finding the integrals, finding the equations of motion. This is now pure mathematics over here. Minus k over m, write it as minus omega square x. You know what the solutions are. It goes something like a exponential I kx plus b exponential minus I kx. This is it, right? And there's also t here, because we are essentially considering it in time. I kxt minus I kxt. Is this correct? As I recall, it should be. Let's see. Since we are only considering, well, x of t to be, what do you call it, real, it is only real, you don't need to consider the complex results that will come from the signs of it. So you could simply write this entire thing as a cos omega t. I think here we should, that is exactly what we should do. Oh my bad, it isn't k, it's omega. As confusing it with the wave number that we use in quantum mechanics. A cos omega t plus b sine omega t. So you can replace that with a phi here. And this is x of t. So this was a pure mathematical integration. Do not need to consider the complex counterparts of it, because this is x of t is really a real function alone. So here we actually integrated the equations of motion and we found what the motion of the system is, and which means what x of t is. Oftentimes, a lot of times when you solve the mechanical equations, and when I have solved it until now, I've left things up to here only. This is called reducing the problem to quadratures, which is that you have found what the differential equations are, you have found what the equations of motion of the mechanical system are, and that is where you left it, because, well, the rest part is pure mathematical solution, pure mathematical manipulation of solving differential equations. So it isn't exactly the kind of, here we didn't exactly do a physics. We saw a differential equation, we recognized what the solutions of this kind of differential equations are, we recognized the solution, so we basically wrote down the solution. This is purely mathematical, there's no doing physics here. Which is why oftentimes we reduce the problem to quadratures and say that, well, mathematicians can go ahead and solve this, or that you can solve this on computer, you can solve this numerically. So that's the kind of thing that we do. But since this video was about integrating the equations of motion, I figured that we should, for one matter, solve this kind of thing. And when I say integrating the equations of motion, I will not always mean that actually solving the quadratures. A lot of times we really do reduce the problem to quadratures, and when I will say integrating the equations of motion, I will mean exploit laws like conservation of energies and such, and actually when we carry out the integration, we'll try to derive some useful physics from it. That is what a lot of times I will mean. So we'll want to actually find out not just what the equations of motion are, but mess around with some physics of it, maybe use things like Noether's theorem, and we'll try to figure out, well, what other dynamically interesting quantities we can figure out. And a lot of times I will not solve the quadratures exactly. And one of those is this example that we figured what time as a function of energy would be for a given potential energy. So that is one integration of the equations of motion. And it's an exact second integration, because energy conservation is the first integration and we integrated that again. So this is a second integration. Let's use that law here, shall we? Or use that formula here. This is the potential energy that we are dealing with, and in fact I will solve this exactly as well, but I just want to show you what it can tell you. This should tell you that given there's a system started with energy capital E, which you know, for it to complete one oscillation, this is to go from point x1 to x2. Should we call point x1 simply point 0? That is where the block is at 0. That's what we label it. That's when the potential energy is 0. This is the amplitude point of oscillation. Dx over the square root of E minus half kx squared. Looks good. I can consider twice of E minus kx squared over the whole root. So 2E minus kx squared over the whole root taken up, it comes outwards. So it's now 2m, 2 root m. And this thing over here. Now you figure that, well, this is the time period and it's this constant, the integral from 0 to a of this particular thing over here, and you might figure that the time period should somehow depend on the amplitude, but as I recall, it does not depend on the amplitude. And how do we get that result? Well, not by simply looking at this expression, but we have already talked about mechanical similarities, and since the given potential energy is here a homogeneous function of the coordinate and it is homogeneous with degree 2, I have we have discussed this in the previous video, and I think it was the last video only. I have discussed it in the last video that scale transformations of coordinates for homogeneous functions of potential energies will transform other dynamical variables, and that is including time as such. L is the linear dimension that is getting transformed, that is getting scaled up, and I think this was the result, 1 minus half k. K is the degree of homogeneity of potential energy function. I even discussed this particular example in the last case, 1 minus 1, 0. So this basically comes out to be 1. So even if you scale the amplitude in this particular case, you don't scale the time period anyhow. Thus the time period is really independent of what the amplitude is. So now you can go ahead and solve this, and what result should you get? Well, since in the last case, when we solve the Lagrange equations, which really were Newton's equations, and we actually got this result. Let's consider phi equals 0. In fact, what would phi equals 0 imply? I think phi equals 0 would imply phi is 0, so you put t as 0, and we assume that t equals 0 is when the motion began. So this would give you 0, and the system is at its extreme point, and that sounds good to me, that we have started it with such extreme point. So in that case, phi is in this particular case 0. What you do is cos of omega t is equal to x over capital A. So cos inverse omega t should be the cos inverse of x over capital A, and thus that tells you that t is 1 over omega cos inverse of x over capital A. Now if we talk about when x equals A, for that matter, this cancels out this time period, then this basically becomes the time period, no? Because when x again equals A, so that will basically tell you that what is that other time instant? What is that other time instant when x equals A? Because it equals A when t equals 0, for that matter, so that's one thing. And so this will basically tell you something like the time period, that x again equals A at this. But it should not exactly tell you time period, because time period would be that when it equals this again, and then it goes back to this point. So it gives you half of the time period. And so I'll simply double it, and this will give me 2 over omega. And that looks good to me. And this cosine inverse of 1 is what? It's 0. Perfect. So the time period is 2 over omega, and yes, that's perfect. And I hope there isn't any pi I'm missing. We typically see capital T as pi over omega, but that would have to do more with these phase constant. I hope I haven't missed the phase constant. Or have I? When I put t equals 0 over here, cos of 0 is equal to 1. Alright, sounds good to me. So in this particular case, I looked at the solution of Lagrange equations for this particular case, and then I figured out what the time period for this particular case would be. On the other hand, I could have solved this integral, and I would have found what the time period of oscillation would be. So, and in that case, I basically inversed the equations of motion to found the inverse function that would tell me what time period should be. So how is exactly this function, this expression valid? Well, for a lot of cases, we cannot even finding the equations of motion would be difficult enough. You can only inverse the equation from x of t to t of x when you know what the equation exactly x of t is, and in a lot of cases we can't do that. Not even, and that is if you try numerical simulations, if you try solving the differential equations numerically, you don't exactly have an analytical function, do you? And if an analytical function, let's say, does not exist that solves those particular equations of motion, the analytical solution does not exist, and you have to resort to solving it numerically. So you cannot have an inverse function that will tell you that. But how about this? So even if the analytical solution does not exist, you can numerically solve, because we already have an integral. In that case, we don't even have an integral. The numerical thing has taken that thing out of the picture. But here, since we have an integral, you can solve this integral numerically, and you can figure out roughly what capital T for a given initial condition, that is starting with a value of energy capital E, should be. So this is exactly why this formula is so useful. Most of the cases you will not be able to find the inverse function T of x and will be able to figure that out. But using this formula, we can. And this isn't just valid well for oscillatory motions, that is, it will tell you the time interval to go between any two such points. And you'll have to figure out by the form of the potential energy function what motion is oscillatory, what motion is forbidden, because you might end up putting limits over regions where the motion is forbidden. It does not execute that, so it will not give you a proper answer. It may, I suppose I've never actually tried it because I'm careful with whether the motion is forbidden or not, but I suppose it will be fun to try. I'm guessing it will give you negative answers and it will give you imaginary answers and such. The answers will be, for all physical purposes that have been considered here, meaningless. So you need to consider the form of the potential energy and thus accordingly what the allowed regions of motion are. What the regions of allowed motion are. So that concludes our discussion on how we actually start integrating the equations of motion. In the next videos, we'll consider more example and actually integrate the equations of motion. The harmonic oscillator I took here as an example. We'll properly study the theory of small oscillations in the next videos further after covering some of the integrations of the equations of motion. And that was all for today's video of mine, and thanks to all of us.